Good afternoon, everyone. Am I audible? Okay, welcome to the next problem-solving session for the course Fundamentals of Food Process Engineering. So, in this course, in this week, we'll be discussing problems related to week 3 syllabus. So, if you had gone through the week 3 syllabus, it majorly contains thermal processing of food, that is, sterilization, thermal deactivation of microbes, and such concepts. So, in this session also, we'll be discussing problems related to that, and majority of these will be numerical problems. So, even in the assignments, and so you can expect numericals a lot. So, in this problem solving session, we'll have a lot of numericals, and it would be much easier if you guys have a calculator with you, or if you feel that something needs to be repeated, kindly let me know, unmute yourself or post it in the in-call messages. We'll take up that sum again. I'll repeat the question. So if you guys have any doubts, or if you know the answer to the question, you can post it in the in-call messages as well. So we'll start with the questions. If you guys are solving the problems, let me know. We'll go a little bit more slower also. So question 1. Lumped parameter analysis is applicable when a Biot number is greater than 0.1, Fourier number is greater than 0.1, Biot number is less than 0.1, Fourier number is less than 0.1. So before we go into the answer of this question, where is lumped parameter analysis used? Any clue? Am I audible to you guys? Is the Wi-Fi really bad? I'm not sure. But anyways, the recording would be available to you guys. But yeah. So lump parameter analysis is used when you are dealing with transient heat transfer or unsteady heat transfer. That is, when you suddenly subject an object to a different environment with a different temperature, it will take some time for the object to reach that equilibrium temperature. So within that, before that time, there will be an unsteady heat transfer. That is, the temperature will keep changing with respect to time. The temperature of the object will slowly keep changing with respect to time, and after a certain time, it will reach a constant temperature. That is when equilibrium is reached. But before the equilibrium is reached, you will have a lot of unsteady heat transfer happening. And in that case, we use this lumped parameter analysis to figure out what is exactly the temperature of the body at the center or at different locations inside the body. So we use lump parameter analysis to, in case of unsteady state heat transfer. And one of the major criteria of using lump parameter analysis we'll be discussing right now. But before that, what is the definition of Biot number? What is Biot number here? Yeah, so internal resistance of the heat transfer inside the body divided by the external resistance due to convection. So this is the definition of Biot number. So when you have a body in a particular environment with a different temperature, you will have heat transfer happening, and for that heat transfer to happen, it has to overcome two resistances. One resistance is due to the convection from the atmosphere onto the surface of the object, and the second is the resistance due to internal conduction, that is from the surface of the object to the internal centermost point of the object. So Biot number is equal to resistance due to internal conduction divided by resistance due to convection. And so resistance due to internal conduction is K by L. Sorry, resistance due to internal conduction is L by K, and resistance due to convection is 1 by H. So when you include that, your Biot number is actually equal to HL by K. Resistance due to internal conduction is L by K. Resistance due to convection is always 1 by H. So your Biot number is equal to HL by K. So what happens in a lumped parameter analysis is that you lump all these parameters into a dimensionless number, which is a Biot number, which is why it is also it's known as lump parameters. You have Fourier number, you have a Biot number. All these are lumped parameters that include multiple parameters together to make a dimensionless number. So with these dimensionless numbers, we calculate what is the temperature of the body at a particular location, which is why it is known as lump parameter analysis. So, but before you use lump parameter analysis, there are certain criteria that you need to follow. One of the assumptions of the lumped parameter analysis is that it assumes a uniform temperature distribution throughout the body, which implies that the resistance due to internal conduction should ideally be equal to 0. So if you have a body, at any point in the body, there should be a uniform temperature distribution. That is what the lump parameter analysis assumes. For that to happen, you should not have any resistance due to conduction within the body, which means it should be easily able to transfer the heat. But this is possible only in an ideal situation. When you come to a real situation, you will have some resistance due to internal conduction. So you will have some value for this Biot number. It will not be equal to 0. In an ideal situation, it should ideally be equal to 0, but that is not the case in real situations. So you make sure that the Biot number is as low as possible, which is less than equal to 0.1. Hence the answer is option C. So hope this is clear. What is Biot number and why is it necessary for it to be less than equal to 0.1? So this is lump parameter analysis assumes the internal conduction to be 0. So ideally Biot number should be equal to 0, but in real cases that is not possible. So we assume less than equal to 0.1. If you guys have any doubts, kindly let me know. We'll repeat the question again. So then after this, we'll have a series of numericals. If you have any doubts, stop me there. We'll repeat that part again. So half-life of a reaction that follows first order kinetics is 2 minutes. If the initial concentration is C0, what will be the change in concentration after 5 minutes? So before we proceed, do you guys know what is the half-life of a reaction? At what time would you call it the half-life of a reaction? So it's basically when you have an initial concentration C0, that C0 reduces to C0 by 2. That is, it becomes half of the concentration. That is when you call it half-life of a reaction. So it's pretty straightforward here. But the moment you have something known as half-life of a reaction, it means that your concentration is decreasing. That is something that you need to take care. So for a first order reaction, I hope this is familiar to you guys. This is 11th chemistry. So for a first order reaction, dC by dt, which is the rate, is directly proportional to the concentration. It's basically C power n, where n is the order of the kinetics. So here, since it's the first order, you'll have n equal to 1, which basically means dC by dt is directly proportional to C. And if you remove the proportionality, dC by dt is equal to minus Kc. So can anybody tell me why do we have a negative sign here? Why not just Kc? What is the significance of the negative sign here?
Because concentration decreases.
Yeah, so since the concentration decreases, you have a negative sign here. If we were dealing with a first order kinetics where the concentration was increasing, you will have plus Kc here. So since concentration is decreasing, we have a minus Kc here. So now upon integrating dC by C from C naught to some concentration C at some time t, then we have integrate k dt from 0 to time t. So when upon integration, this is the formula that we get. Natural logarithm of C by C naught is equal to minus kT. So this is a first order kinetics where you have some deactivation or some kind of concentration reduction happening. So this is a formula that you guys need to be very thorough for this entire week's problems. So in this case, how do you find out what is the half-life of a reaction? If this is the formula, so for a half-life of a reaction is the time taken for the concentration to reduce by half, which means now C will be equal to C naught by 2. If that is the case, then when you simplify this, you'll basically get ln 1 by 2 equal to minus kT, and ln 1 by 2 is equal to minus 0.693. So basically your time will be equal to 0.693 by k, where k is the reaction rate constant. Is this derivation clear? You just substitute C equal to C naught by 2. So C naught gets cancelled in the numerator and the denominator. So you have natural logarithm of half, which is equal to minus 0.693. So minus both LHS and RHS will get cancelled. So you'll have T half is equal to 0.693 by K. So we know that the half-life of the system is already given, which is 2 minutes. So from that, we can calculate what is the rate of the reaction. So T half is already given as 2 minutes. So 2 is equal to 0.693 by K. So K is equal to 0.346 minute inverse. So it is the same units as the unit that you substituted for time. If you're doing it in seconds, you will get the answers in seconds. Hope this part is clear. So from this, we need to calculate what is the change in concentration after 5 minutes. The reason why we are doing we are calculating the reaction rate constant is because we would want, if we substitute time t equal to 5 minutes here, and if we know the k, which is the reaction rate constant, we can find out what was the change in concentration. So for that, we already have time equal to 5 minutes, but we did not know what k was, which is why we calculated k from the half-life of the reaction. So from the half-life of the reaction, we calculated k. We already know what T is. From that, we'll calculate the fractional change in concentration. So with the k that we calculated, I'm substituting back into the same equation. So ln C by C naught is equal to minus 0.346 minute inverse into 5 minutes, which is what is the time that is asked to calculate the concentration difference. Then if you take an exponent on both sides, you get C by C naught, or antilog on both sides, you get C by C naught equal to 0.1773. Is this clear? Should I go slow? Are you guys calculating? If you're okay with the pace, just kindly let me know. Is there any part that needs to be clarified again? Okay, so from this, I'm guessing you guys are fine with it. If not, let me know. Okay, so we now know what is C by C naught. What was asked was the percentage change in concentration after 5 minutes. which means you need to know what was the change in concentration, that is C naught minus C. What was the change in concentration divided by the initial concentration into 100. This is how you calculate the percentage change in the concentration. So C naught minus C, which is the initial concentration minus final concentration divided by initial concentration into 100. So if you divide by C naught, you'll get 1 by C naught into 100. So C by C naught is what we calculated right now. So 1 minus 0.1773 into 100, which is coming out to be 82.3%. Answer is option C. Any doubt in calculating from the half-life of the reaction, why we calculated that? Or any other doubts in any of the derivation? So since the half of the class is going to be only numericals, so kindly let me know if you guys want me to slow down or you want to calculate yourself and check for the answer. Okay, moving on to question 3. Reaction following zero order reaction kinetics is given by the following equation. So you have C naught by C is equal to e power minus kt, C naught by C equal to e power kt, dC by dt equal to minus k, and dC by dt equal to minus kc. So let us assume that it's a zero order reaction kinetics where some concentration is decreasing. So if the concentration is decreasing, what will be the answer? Yeah, so C is the answer for this. So for a zero order reaction, dC by dt is directly proportional to C power n. In this case, n is equal to 0 because it's a zero order reaction kinetics. So C power 0 is equal to 1. So dC by dt is equal to minus k. So if you have dC by dt is equal to minus k C power 0, the C power 0 goes to 1. So you will only have dC by dt equal to minus k. So the answer is option C. Now, had this reaction been a first order reaction, what would have been the answer? If the same question was applicable for a first order reaction, which one of these equations is correct? Yeah, that is also correct, and it will also be valid for option B. So basically, if you integrate, you will get option B. So both are right had it been a first order reaction. Okay, moving to question 4. I hope this is clear for everybody, the how to find out the reaction order and reaction rate. Because if you get stuck in some point, if you forget the formula, if you know how to derive that formula, half of the problems will be easy for you guys to answer. So question 4, statement 1, in a first order reaction, there is a linear relationship between the number of survival microorganisms and time. So here we are dealing with microorganisms. We are now shifting our focus to microorganisms because you need to ensure that your food products are without any contamination or pathogens. So we often expose our food to different kinds of thermal processing such as bleaching, blanching, canning, sterilization and stuff. So in those processes, you will have to keep account of the number of surviving microorganisms with respect to time. You will keep on monitoring the number of pathogens with respect to time, and you will expose it to certain heat or steam or some kind of a factor that will kill these microorganisms, and often the death of these microorganisms follow first order reaction kinetics. It's very often that the microorganisms will follow first order death kinetics, which is why the moment you are asked about anything about microorganisms, you can go for first order reaction kinetics. So statement 1, in a first order reaction, there is a linear relationship between the number of survival microorganisms and time. Statement 2. In a zero order reaction, the slope of the straight line obtained by plotting the concentration versus time indicates the reaction rate constant. So which of these is true and which of these are false? So we'll go with statement 1. Statement 1, true or false? Yeah, statement 1 is false. Only the rate of the reaction is directly proportional to the concentration, but the number of survival microorganisms is not in a linear relationship with time. So if you remember what the first order reaction was, it was ln C by C naught equal to minus kT. So which means if I take an antilog, C by C naught is equal to e power minus kT. So you have an exponential relationship, you do not have a linear relationship. It is asking between the number of survival microorganisms, which is C in this case. So the number of survival microorganisms and time will have an exponential relationship and not a linear relationship. So statement 1 is false. So statement 2, in a zero order reaction, slope of the straight line obtained by plotting the concentration versus time indicates the reaction rate constant. So if you plot a graph between C versus T, yeah, so the second statement is true because for a zero order reaction, as we discussed in the previous question, dC by dt is equal to minus k. So which means if you integrate this, you will get C minus C naught by equal to kT. There's a small thing here. C minus C naught equal to kT. So if you assume, so if you plot a graph between C versus T, in this equation itself it's very obvious. If you plot a graph between C versus T, so the slope is equal to the reaction rate constant. So statement 2 is true. Hope this is clear. Moving to question 5. The food product is cooked at 121 degrees Celsius for 12 minutes. The vitamin loss in cooking process follows first order kinetics, and D121 for vitamin destruction is 200 minutes. So what is the percentage vitamin loss during cooking? So when you're dealing with thermal processing of food, you cannot keep on heating the food as however long you want, because first thing is that it will often affect the quality of the food, some taste, some kind of sensory quality, or some kind of sensory qualities might be affected if you keep on heating the food for a long time. And second thing is that it will very often lead to vitamin loss or nutrient loss in the food, which is why just to keep killing bacteria, you cannot keep on heating it. You need to optimize the process so that you are able to achieve the sterility with minimal loss in vitamins. That should be your aim. So in this case, the food product is cooked at 121 degrees Celsius for 12 minutes, which involves a vitamin loss that follows first order kinetics. And D121 is 200 minutes. So what is the percentage vitamin loss during cooking? So before we proceed with this, does anybody know what D121 is?
The time required to reduce the microbial count to log 10.
Yeah. So it's not just applicable for just microbes. It is also applicable for any reduction in concentration of any substance. So even for vitamin, there is a concept known as D, which again is the same definition as you said for microbes, but it is applicable for vitamins. So D value is the time taken to reduce the concentration by 10-fold, which means if you have an initial concentration of C naught, your final concentration C will be equal to C naught by 10. That is 1 log reduction or 10-fold reduction. That is known as the decimal reduction time or D value. So in the first order kinetics, again we look at the same equation that we discussed in the previous slides. So natural logarithm C by C naught is equal to minus KT. So again we have a negative sign because we are looking at vitamin loss. So that is why we have a negative sign here. So in this case, if we have to incorporate D value in this equation, what do we do? We will just change C is equal to C naught by 10. So if we change C equal to C naught by 10, C naught gets cancelled. We will have ln of 1 by 10 is equal to minus KD. We change T to D because when C equal to C naught by 10, that is the time. D value is equal to the time taken. So we change T as D here. And then substituting ln 1 by 10, that is equal to minus 2.303. Minus and minus gets cancelled. So D is equal to 2.303 by K. So this is not just applicable for vitamin loss. This equation is also applicable for any reduction in any of the substances when we are looking at D value. And first order kinetics, that is also important. This is not applicable for anything that follows any other order of kinetics. Only when certain product follows first order kinetics, this D value equation is consistent throughout, irrespective of what we are looking at. So D is equal to 2.303 by K. So now that we know how to calculate D value, what is the next step here? How do we calculate what is the percentage vitamin loss? What is the next step? So we know what the D value is. It is given as 200 minutes. So if we substitute 200 minutes here, we will get K or the reaction rate constant. So with the reaction rate constant, we can substitute back in this equation. We know what is the time taken for the cooking process, which is 12 minutes. With that, we can find out what is the fractional change in concentration. It is very similar to the previous question that we tried, where we were looking at the change in concentration. It's very similar. There we used half-life of a reaction. Here we are where the C equal to C naught by 2. Here we are looking at the decimal reduction time, which is C equal to C naught by 10. So those are two different concepts, but the overall approach is the same. First we find out what is the reaction rate constant. From there we substitute and find out what is C by C naught. So when you substitute D value is equal to 200 minutes, we have 2.303 by 200, which is equal to 0.0115 minute inverse. So with this K, I am going to substitute back in this equation. So ln C by C naught is equal to minus 0.0115 into 12 minutes, which is the cooking time. So your RHS becomes minus 0.1381. And if you take an anti-log on both the sides, you have C by C naught equal to 0.871. I hope this part is clear. This is similar to the previous question that we solved. If there is any doubt, if you guys want me to go slow, please let me know. So again, C naught minus C by C naught into 100 will give me the percentage change. So 1 by C by C naught into 100. I am dividing the equation by C naught. So you have 1 minus C by C naught into 100. So the percentage change is equal to 1 minus 0.871, which we calculated here, into 100, which is 12.9%. So answer is option B. There was a 12.9% vitamin loss when the food was cooked for 12 minutes. Given that the reaction rate constant to followed first order kinetics and the decimal reduction time was 200 minutes. So when you have a decimal reduction time, this is how you calculate the reaction rate constant. Hope this part is clear. So for micro, in this case, when you want to look at relationship between microorganisms, when you just substitute this value, the fact that t equal to 2.303 by k, if you substitute the values, you will actually get log n naught by n equal to t by d. You substitute the value of k here. K is equal to 2.303 by d. So if you substitute 2.303 by d here, your ln is actually will become log. You can change it to log by multiplying it into 2.303. If you guys are aware of that, a natural logarithm can be changed into log to the base 10 if you multiply by 2.303. So you have 2.303 log of c by c naught equal to minus 2.303 by d into t. So this is the equation that you get. Please note when it is natural logarithm, when it is log to the base 10. Otherwise, the numericals that you calculate will come out to be wrong. Okay, hope is this clear when it is log and when it is ln? If you guys are very doubtful, you can start from the derivation of the first order kinetics in order to avoid confusion. But if this is the formula that you guys are going to use, please know that this is log to the base 10. Is there any part that needs to be repeated so far in any of the questions? Okay, question 6. The slope of the survivor curve can be used to estimate A, the reaction rate constant, B, the Z value, C, the F value, and D, decimal reduction time. So are you guys aware of what is a survivor curve?
No, ma'am.
Okay, we look at this first. So a survivor curve is basically when you're as I said, when you're processing the food, you need to keep account of how many microorganisms are still surviving in that food. So your when you plot a graph, you will have number of survivors on a log scale. That is number of pathogens that are still inside your food on a log scale versus time. So when you have number of survivors or number of pathogens remaining per time, this is known as a survivor curve. That is n, number of survivors is basically n, and then this is with respect to time. This is known as a survivor curve, and as you guys remember, the decimal reduction time is the time required to reduce the number of microbes or survivors by 1 log cycle or a factor of 10. So basically, if I had 10 power 6 or 10 power 5 organisms initially at a particular time, the amount of time it requires to reduce from 10 power 5 to 10 power 4, that this time is known as the decimal reduction time. So it is much more clear if you probably look at the graph. So from 10 power 5 to 10 power 4, it took a particular amount of time. So this value is known as the decimal reduction time. And this plot is known as the survivor curve or the survivor plot, number of survivors with respect to time. So the slope of the survivors, as you can see here, can be used to calculate the d value. So you actually get 1 by d if you plot logarithm of n naught by n with respect to time. If this is in the form of y equal to mx, this form of a straight line that passes through the it is the form of a straight line where it is y equal to mx, and your slope is actually equal to 1 by d. So if you take the inverse of the slope, you can actually calculate the decimal reduction time. So the answer to this question is the decimal reduction time. From the slope of the survivor curve, you can use that to take a reciprocal and then calculate the decimal reduction time. Is the decimal reduction time concept clear? Any doubts in that? Time required to reduce the number of microbes by 1 log cycle or a factor of 10. So this is also a formula that you can follow. This is basically the same thing I've written here, but D is equal to delta T, which is the change in time, divided by log N1 minus log N2. Here it's just the same thing but in different notations, that's all. So we know what is D value or decimal reduction time. What is Z value and what is F value? So we'll first start with F value. F value is also known as the thermal death time, which means that it is the total time required to accomplish a stated reduction in the microbial population at a given temperature. So in order to make it more clear, let's say I want to reduce the microorganisms from 3000 to say 5 microorganisms. I had 3000 microorganisms in my food. I want to reduce it to 5 microorganisms finally. So what is the time taken to reduce from 3000 to 5 at that particular temperature, at a single temperature? That is known as the F value. So basically you can actually directly substitute T as F. T is equivalent to F in this case. When I give you N naught, when I give you N and I ask you to find out the time is also known as the F value or the thermal death time. So decimal reduction time is D, thermal death time is also is known as F, but you can substitute it here in the form of T. Both are same here. Any doubts here? Any confusion? So in thermal death time, it need not be any log cycle or anything. It can be literally any number. Whatever reduction that you want to make it happen, the time required for that reduction is known as the F value. Okay, moving on to Z value. Any clue what Z value is?
It's a temperature that is required to reduce the microbial count to factor 10.
That is D value. What you are stating here is D value. What is F value then? Temperature is
Temperature, ma'am.
yeah, but then it's not exactly micro. No, we're not looking at microorganisms reducing by 1/10. We're looking at D value reducing by 1/10.
Okay.
So the temperature change required to reduce the D value by 1 log cycle is the 1 log cycle is known as the Z value. So if the same curve, if I plot D versus time instead of number of survivors, if I plot D versus time on a log scale, then the slope, then the inverse of the slope is equal to the Z value. So the same here, if I let's say if I have D here and I have time here, and I had some D value as 10 minutes, and let's say I had here 1 minute. So the temperature required to reduce the time from 10 minutes to 1 minute is known as the Z value. We'll be a little more clear when we look at the coming problems. So D value is time, the decimal reduction time. Thermal death time is also basically time, but for any stated reduction in the microbial population. Z value is the temperature change. So when you increase the temperature, naturally your death kinetics will also be faster. So the amount of time you need to expose your food will also reduce. So the temperature change required to reduce the time by 1/10, the decimal reduction time by 1/10 is known as the Z value. So I hope this is clear, but we'll keep discussing about these parameters time and again. So I hope it will be much more clear in the coming problems. Question 7. The D naught value and Z value of an organism, microorganism, is 0.8 minutes and 11 degrees Celsius respectively. Calculate the thermal processing time required for 10 log cycle reduction of the same microorganism at 130 degrees Celsius. So before we go forward, what is the difference between D value and D naught value? What is the difference between D and D naught? So D value can be calculated for any temperature. The moment you have a naught in the subscript, it is calculated only at 121 degrees Celsius. So it's like a standard temperature here. So D naught, F naught and all those, the moment you have a naught here, it is calculated at 121 degrees Celsius. So here the D naught value is actually given for 121 degrees Celsius, which is 0.8 minutes. Okay, and we need to, we have the D naught value at 121 degrees Celsius. We have the Z value that is constant for a particular microorganism, which is 11 degrees Celsius. We need to calculate the thermal processing time, which is time T or F value basically. We need to calculate the thermal processing time required for 10 log cycle reduction of the same microorganism at 130 degrees Celsius. So how do we proceed with this? So as I said, Z value is the temperature change required to reduce the D value by 1 log cycle. So this is the graph I was talking about. If you have D value in the y-axis in the logarithmic scale and you have temperature on the x-axis, so the temperature required to change by 1 log cycle, that is if you want to reduce it by 1/10, so from 10 to 1, let's say, I'm giving an example. So if you want to reduce the D value from 10 to 1, what was the temperature change required? That is known as the Z value. So Z value is basically the inverse of the slope, which is T2 minus T1 divided by log D1 minus D2. Is this clear? The inverse of the slope. So this is a very important formula which we will be keeping on using throughout almost majority of the problems. So I'm just simplifying the equation. T2 minus T1 divided by log D1 by D2. Is this clear? Any doubt in this? D value is for number of microorganisms fold reduced by 1/10. Z value is the temperature where the D value is reduced by 1/10. So it's going to be a bit confusing, but the more problems you solve, it's going to be a bit more clear. So now we know the D value for 121 degrees Celsius. We have to calculate at 130 degrees Celsius. So we know two different temperatures. We know one of the temperature is 121 degrees Celsius. The second temperature is 130 degrees Celsius. One of the D value is given and we know the Z value. With that, we can calculate the other D value. So I'm just simplifying this further. Log D1 by D2, I'm taking this to the LHS, is equal to T2 minus T1 divided by Z. So now I'll be substituting the values here. I'm taking an anti-log on both the sides, which is D1 by D2 is equal to 10 power T2 minus T1 by Z. And we have given D1 is equal to 0.8 minutes, which was actually D naught in the question. So that is 0.8 minutes. And the moment you say you have a naught in the question, which means that the temperature that was used to calculate was 121 degrees Celsius. So sometimes it will not be mentioned in the question. You need to know which one is calculated at 121 and which one is not. So T1 is equal to 121 degrees Celsius. Z value is given as 11 degrees Celsius. We need to calculate at 130 degrees Celsius. So that is equal to T2. Is this part clear? Anything that needs to be repeated? From which part is it confusing?
I think it's clear only, ma'am.
Okay, thank you. So yeah, so we substitute the values here. 0.8 by D2 is equal to 10 power 130 degrees Celsius minus 121 degrees Celsius by 11. So in this case, you can choose to substitute in degree Celsius itself because you're taking a difference. But if you if you are confused when to use it in Kelvin, when to use it in degree Celsius, safe side, substitute all the parameters in SI units itself, which is in Kelvin. The answer will be the same in this case if you either substitute in degree Celsius or Kelvin. So I am here substituting in degree Celsius itself. You can do it in Kelvin as well. So 0.8 by D2, this comes out to be 6.579. From this, I can calculate what is the decimal reduction time at 130 degrees Celsius, which comes out to be 0.121 minutes. Is this clear so far? So why am I calculating decimal reduction time? The question asked was the thermal processing time, which was F value. Why am I calculating the D value here? So that we can substitute back in this equation. Log of N naught by N equal to T by D. In this case, thermal processing time F value is also here time T. It's the same thing. So now we know the D value for at 130 degrees Celsius. We were already given that it was a 10 log reduction cycle. With the moment you call it as 10 log reduction cycle, then the log N naught by N will entirely become equal to 10. Had it been a 4 log reduction cycle, your LHS will be equal to 4. Had it been a 3 log reduction, it will be equal to 3. So in the question, it was given 10 log reduction cycle, which means your LHS, the log reduction is equal to 10. So 10 is equal to T divided by 0.121, which is calculated at 130 degrees Celsius. So time equal to 1.21 minutes. So the answer is option A. This is clear. So you need to make sure the moment you call you see the word time, it is not exactly the decimal reduction time. You need to see whether what is asked, whether it is the F value that is asked or it is the D value that is asked. Both are times. So you need to read the question carefully, figure out which one is calculated at 121 degrees Celsius, and then proceed with the question. Is this part clear? Any doubts? So if you see max to max, you will have this equation coming in and this equation coming in back and forth. So it's majorly these two equations that you will have from a lot of questions. Apart from that, you will also have other equations, but these two are the main. Okay, moving to question 8. A food product is sterilized in a retort, which is basically like an autoclave where you maintain very high temperatures to sterilize the food. The time and the corresponding temperature in the center of the can is given in the below table. Calculate the F naught value if Z value is 10 degrees Celsius. So here F naught value is basically at 121 degrees Celsius. The moment you have a naught, you're talking about at 121 degrees Celsius. If the Z value is 10 degrees Celsius, F value is basically the time. So any clue how to proceed with this? So here we will be introducing a slightly newer concept. Apart from the D and Z value, we'll introduce something known as the lethality factor. So lethality factor is the time taken at 121 degrees Celsius to attain an equivalent sterilization value as 1 minute at another temperature. Which means that, let's say at 130 degrees Celsius or so, and within 1 minute, I am able to reduce the microorganisms from 100 to 50. It's just a random example I'm giving. At 130 degrees Celsius, within 1 minute, I am able to reduce the microorganisms from 100 to 50. So the same 100 to 50, how much time is it taking at 121 degrees Celsius is known as the lethality factor. I hope this is clear. So the moment you talk about time at 121 degrees Celsius, it is automatically F naught value. So So if you have to calculate how to calculate numerical lethality factor, there are two different methods that is described in the lecture videos. One is the graphical method. The other one is the numerical integration method. So either you can plot a graph and figure out, or you can do a numerical integration where you just sum up the values. So lethality factor equal to F naught is equal to summation of L into delta T. So L is the lethality factor that you need to calculate, and delta T is the time intervals are already given in the table. For every 5 minutes, the temperature was recorded. So it's a very uniform interval if you see 0, 5, 10, 15. So delta T is 5 minutes here. Every 5-minute interval you're taking a reading. But at every 5 minutes you need to know what is L so that you can calculate F naught. But we only know what is the temperature of the food product given. So in order to calculate lethality factor, this is the equation. L is equal to 10 power T minus T naught by Z, where T naught is 121 degrees Celsius. Again, the moment you have a naught here, it is generally 121 degrees Celsius. So I'm proceeding fast because this problem involves a lot of calculations, but I'll tell you how to calculate. So for each and every minute, you have the temperature given, and you know what is the formula for calculating the L value. So lethality factor is equal to 10 power T minus T naught, which is 121 degrees Celsius, and Z value is already given in the question as 10 degrees. So you substitute T naught as 121, Z as 10, and for each temperature you will calculate L. For 0 minutes you won't do it, but for each and every temperature you will calculate the L value. Then, as I mentioned, F naught is equal to sigma L delta T. So since delta T is constant, we can take it out of the summation, which is equal to 5 minutes, into summation of L, which means you will add up all these values, L values. If you add up all these L values at each and every time point, then you get it as 0.865. So 5 minutes into 0.865, which is delta T into summation of L, will give you F naught, which is equal to 4.325 minutes. Is this clear? Is there any doubt in this? So the moment you have a sum where you have the time given, the temperature at a particular point in the food is given, and you're supposed to calculate the thermal processing time or the F naught at 121 degrees Celsius, this is the formula that you'll be using. The lethality factor concept is what you'll be using. Is this part clear? How to calculate L? You calculate L for each and every time point, multiply it with time. If the time is constant, you can take it out. If the time is not constant, you will have to multiply L into delta T, and then you add it to calculate the F naught.
Ma'am, we are adding all the values of L, ma'am.
Yeah.
Yeah. Okay.
Yeah.
Thank you.
So delta T is constant, so you need not add it. You can take it out, but you have to add all the L values at each and every temperature. So summation, this is basically equal to 7.94 into 10 power minus 8 plus 2.51 into 10 power minus 4 plus 0.025 plus 0.79 plus 0.05 will give you 0.865, which is equal to, now the F naught value is equal to 4.325 minutes. So generally, so far in the past 2 years, there has been one question similar that involves the lethality factor. Majority of them include the first order kinetics that we have been discussing so far. It so happens that in the assignment, generally we have one question regarding the lethality factor. I'm not sure about this year though, but for the past 2 years, there has been similar question related to this. Okay, moving to question 9. The microbial growth is assumed to follow the first order kinetics. So, both in case of growth and death, microbes follow first order kinetics. It's a general assumption. Unless and until stated otherwise, you can assume both the growth and death to happen in a first order kinetics reaction. If the microbial count doubles in 3 hours, how much time is required for the microorganisms to grow 4 times? So how do you proceed with this? So anytime the moment you talk about first order kinetics, it is always best to start with the first order kinetics equation. From there, you can substitute the values and figure out what is required. So we already know that the microbial count doubles in 3 hours. Here, if you see, the negative sign is removed because we're talking about growth here. The concentration is increasing. So there is no negative sign here, it's a positive sign. So you need to make sure what we are looking at. We are looking at loss or we are looking at growth. Here, one thing I need to mention, here N naught is different. This is not at 121 degrees Celsius. This is just initial concentration. All other values like temperature, D value and all, the moment you have a naught, it basically means 121 degrees Celsius. In this case, this naught is different. This is just for the initial concentration. If you want, you can make it as NF and NI. It's up to you guys. So don't get confused between this naught and the naught that we've been discussing so far. So ln natural logarithm n by n naught is equal to kt. One more thing that we need to understand here is n here is the count or the number of microorganisms. It is not the concentration of microorganisms. So when you are given the concentration, unless and until the volume remains the same or so, do not substitute the concentration in this equation. Always substitute the amount. So when the microbial count doubles, n is equal to 2 times n naught. That is, it becomes twice the initial concentration. So you substitute that, n naught gets cancelled. You have ln2 is equal to k into t. The moment you substitute ln2 is equal to k into t, we already know that this doubling happens in 3 hours. So I'm substituting time is equal to 3 hours. So k comes out to be 0.231 hour inverse. That is ln2 divided by 3. That comes out to be 0.231 hour inverse. So now we know the k. And we have to calculate the time t when the microorganisms grows 4 times. Which means that now n will be equal to 4 times n naught. So that's what I'm going to do here. N is equal to now 4 times n naught. We calculated what is k. So yeah, I'm substituting n is equal to 4 times n naught. N naught gets cancelled. So ln4 is equal to k into t. So ln4 is equal to 0.231, which is the reaction rate that we calculated, into time. So when you calculate the value, you get time is equal to ln4 divided by 0.231, which is equal to 6 hours. Is this clear? So in case the moment you have something known as first order kinetics, first make sure whether it is loss or a gain in concentration and start from there. Start from the equation. It will be much easier to solve the problems. Okay, question 10. Only one microorganism survives in 10 power 12 microorganisms when subjected to heat treatment for 5 seconds at 140 degrees Celsius. Find the Z value of this microorganism if its D naught value is 1.25 minutes. So we know what is N here. N, final number of microorganisms, is only 1. N naught was 10 power 12. That is in only 1 in 10 power 12 microorganisms, which is basically you had initial 10 power 12 microorganisms, which is N naught. Now you have only 1, which is N, and you subject it for a heat treatment of for 5 seconds, which is equal to your time T. And your capital T, which is the temperature, is 140 degrees Celsius. We need to calculate what is the Z value if D naught value, that is the D value at 121 degrees Celsius, is 1.25 minutes. So how do we proceed with this? We again start with first order kinetics, which is ln n naught by n is equal to t by d. You can either have it as kt, but ln, when it is k and when it is d is something that you guys need to take care. When it is ln here or natural logarithm, you have equal to kt. When you have log here, you can change it to t by d. Please make sure what your equation is. So I have n naught is equal to 10 power 12 and n as 1. My time is given as 5 seconds and d is something we do not know. This d value is for 121 degrees Celsius. It is not for 140 degrees Celsius. So I am calculating what is d at 140 degrees Celsius. So log 10 power 12 is basically 12. So 12 is equal to 5 by d. So d is equal to 5 by 12, which is equal to 0.416 second. Is this part clear?
Yes, ma'am.
So now we know the d value at 140 degrees Celsius. We know d value at 140 degrees Celsius. We know the d value at 121 degrees Celsius. So we have two different temperatures. We have two different d values. From there, it is easier to calculate the z value. If you guys remember what the equation for z is, d1 by d2 is equal to 10 power t2 minus t1 by z. Or else you can start from the d versus t graph also. So if you have a logarithmic scale of d and you have temperature on the x-axis, then the inverse of the slope is actually the z value. You can do it that way as well. But when you simplify the equation, this is what it will come down to. So 1.25 is given in minutes. So I'm converting it in seconds for uniformity. So 1.25 minutes into 60 to convert it into seconds, which is equal to 75. And d2, this is what we calculated at 140 degrees Celsius, which is equal to 0.416 seconds. That is equal to 10 power. T2 was 140 degrees Celsius. T1 is 121 degrees Celsius divided by Z. So Z is what we need to find out. So when I simplify this further, I get 180.28 is equal to 10 raised to 19 by Z. So my Z value comes out to be 8.44 degrees Celsius. That is, you need to increase the temperature by 8.4 degrees Celsius in order to reduce the D value by 1/10. So I hope this is clear.
Yes, ma'am.
These PPTs and all will be made available to you guys, so you can refer back to these solutions time and again whenever you want. Okay. Question 11. The activation energy of a first order reaction is 50,000 joules per mole at 30 degrees Celsius. Calculate the temperature at which the reaction rate doubles and assume a value of the gas constant as 8.314 joule per mole Kelvin. So should be a relatively simpler problem. How do you proceed with this? What is the equation that we use?
Arrhenius equation.
Yeah. So the moment you have a reaction rate differing with temperature, a first order reaction rate generally follows the Arrhenius equation, which is equal to K is equal to, which is the reaction rate constant K is equal to A e power minus EA by RT. So A here is the Arrhenius constant. EA is the activation energy that is mentioned in the question. R is the universal gas constant and capital T is the temperature. So Arrhenius equation is actually K equal to A e power minus EA by RT. So if you know that two different temperature and two different rate constants, you can easily calculate what is the activation energy, or the same way, if you know all the other parameters, you can calculate the one parameter that is remaining, provided it is mentioned that the reaction rate varies with temperature. So let's take one K1 is equal to A e power minus EA by RT1. At T1 the reaction rate is K1. Let's assume that, and I'm taking a log on both the sides. So log K1 will be equal to log A minus EA by RT1. So same way for some other temperature T2, K2 is equal to A e power minus EA by R T2. I'm taking a log. So log of K2 is equal to log A minus EA by R T2. Now I'll be subtracting this equation from this equation, which means now it will be log K1 minus log K2 in the LHS. Log A minus log A will be cancelled, will be equal to 0. So then I'll have EA by R T2 minus EA by R T1. I hope this part is clear. Basically, I'm taking a log and subtracting these equations. So I'm just simplifying this further. So the log K1 minus log K2 can be written as log K1 by K2 is equal to EA by R 1 by T2 minus 1 by T1. Now if I take an we don't have to take an anti-log, but that's okay. Okay. So we already know we are asked what is the temperature at which the reaction rate doubles, which means that K2 is now equal to 2 times of K1. The reaction rate doubles. So K2 is equal to 2 times of K1. Activation energy is already given in the question, which is 50,000 joule per mole. Temperature is given in degrees Celsius. We need to convert here. We have to convert it into Kelvin. T1 is equal to 30 plus 273, which comes out to be 303 Kelvin. So in order to avoid confusion, you can always use Kelvin in all of your numericals. So now we substitute this log of K1 by 2 into K1. So K1 gets cancelled. You'll have log 1 by 2 in the LHS is equal to 50,000 divided by 8.314 into 1 by T2 minus 1 by T1, which is 303. Now if I simplify this further, I get 1 by T2 is equal to 0.0032. Which is equal to which means that temperature is equal to, we'll get it in Kelvin. We'll have to convert it back into degrees Celsius, which is coming out to be 39.5 degrees Celsius, which is very close to 40 degrees, which is given in the option. So the answer is option B. I hope this part is clear. Arrange these equations. Okay. So this is clear. We'll move on to question 12. The D values of microorganisms at 121 degrees Celsius and 135 degrees Celsius are 1.25 minutes and 0.12 minutes respectively. Calculate the total processing time for 99.999% of reduction of the microorganisms at 130 degrees Celsius. So we have two different temperatures, we have two different D values. For 99.999% reduction, from there we can calculate what is N by N naught. From this value we can calculate what is N by N naught, but we need to calculate what is T at 130 degrees Celsius. So first we'll write the given. This is a bit longer problem. We have temperature T1 as 135 degrees Celsius. We have D1 as 0.12 minutes. We then at 121 degrees Celsius, we have D2 as 1.25 minutes. For a different temperature at 130 degrees Celsius, we need to calculate what is the processing time small t. So N here, it is given that it is 99.999% reduction. So N is equal to 1 minus 0.99999. Basically, I'm converting this, I'm removing the percentage. So what is left is 1 minus of this value. N and N naught are always the surviving microorganisms. It is not the microorganisms that died. It's always the remaining microorganisms. So if 99.999% was killed, then left is 1 minus this value. And again, just to give you a repetition of what Z value is, if you plot D in a log scale versus temperature, the inverse of the slope is equal to the Z value, which is delta T divided by log D1 minus D2. Here delta T is temperature. And if I simplify this, I'm getting D2 by D1 is equal to 10 power T1 minus T2 by Z. So if I'm substituting the values here that is given in the equation, from there I can calculate the Z value. Why I'm calculating Z values? Because I need to calculate what is the D value at 130 degrees Celsius. Now at 130 degrees Celsius, I have no clue what is the reaction rate. I do not know what is the decimal reduction time. I have no clue what is any of the parameters. I have only the temperature and the number of changes in the microorganisms. But we need either K or D to proceed to calculate what is the time. So I'm trying to calculate the decimal reduction time at 130 degrees Celsius. From there, I'll calculate the processing time required. So we'll proceed with this. First, I'll substitute the values D2 as 1.25 minutes, D1 as 0.12 minutes, and 10 power 135 degrees Celsius minus 121 degrees Celsius divided by Z. If I simplify that further, I'm getting Z is equal to 13.65. I know these are a lot of numericals, but these are all possible numericals that have been asked in the past 2 years. So it will be very helpful for you guys if you are able to practice this and understand this. So now that we know the Z value will remain constant for a particular microorganism. It will not change with respect to temperature and all. It doesn't make sense. So Z value is constant for a particular microorganisms. So with that Z value, you can calculate what is the D value at 130 degrees Celsius. So we already have for one particular temperature. At 121 degrees Celsius, you already have what is the D value. So I'm keeping that at 1.25 minutes. I need to calculate what is the D value at 130 degrees Celsius. So now I'm substituting T2 as 130 minus 121 degrees Celsius. Z value is what I calculated from the previous step, which is 13.65. So D2 is now 0.278 minute. So now at 130 degrees Celsius, I have what is the decimal reduction time. So log of N0 by N is equal to T by D or F by D. Both are the same. T by D or F by D. And I already know what is, we do not know what is N0, but we know what is N as a function of N0. So if you remember, N was 1 minus 0.99999 of N0, which is equal to 10 power minus 5 of N0. So that is what I am substituting here. N0 I am keeping same. N is equal to 10 power minus 5 of N0. N0 gets cancelled. We now know what is the D at 130 degrees Celsius, which I am substituting here. So now you'll know the T or the F value at 130 degrees Celsius, which is coming out to be 1.39 minutes, and this is what was asked in the question. So it's a longer sum, but then with what you have given, you can always calculate either by the first order kinetics or this equation. Basically, we'll be using these two equations back to back. So with these two equations, you can calculate the D value at a different temperature and then the processing time at that temperature. Hope this is clear. Question 13. A food product is sterilized in a retort. This is very similar to one of the previous question that we calculated, but instead of uniform time, we have different time intervals. That is, we do not have a uniform time interval here. The time and the temperature at the center of the can is given below. Calculate the F0 if the Z value is 10 degrees Celsius. It's very similar. When we use the concept of lethality factor, we calculated lethality factor at each and every time point. We summed it up and then we calculated the F0. Similar concept here, but then we do not have delta t as constant. Suddenly we have 25 minutes here, we have 25 minutes here, we have 20 minutes here. So in this case, what we're supposed to do is that this is basically the same definition that I've given here. Lethality factor is the time taken at 121 degrees Celsius to obtain a sterilization value equivalent to 1 minute at some other temperature T. So lethality factor can be expressed by L is equal to 10 raised to T minus T naught. T naught is 121 degrees Celsius divided by Z. So we calculate L at each and every time point. We multiply it into delta T and sum it up. That is what we're going to do here. Or the graphical method. We were solving the numerical method so far. The graphical method is basically you calculate the lethal rate L at each and every time point. You plot it with respect to time and you calculate the area under the curve. That area under the curve will give you F naught. That is also another way. But in order to simplify further, we are using the numerical method, which is F naught is equal to summation of L into delta T. So now since delta T is not constant throughout, we will keep multiplying delta T and then summing it up. Previously, we took out delta T outside the summation. We added only the L values and then we multiplied by delta T. Now here, since the delta T is not constant or is not the same value throughout, we will multiply L into delta T first and then add. So in first case, the delta T is 25 minutes. In this case also delta T is 25 minutes. In this case delta T is 20 minutes. So F naught is equal to 25 minutes into 10 raised to 70 degrees Celsius, which is the temperature at the center of the can, minus the reference temperature 121 degrees Celsius divided by the Z value, which is 10 degrees Celsius given in the question. Plus, this is for the second data point, 25 minutes into 10 power 95 degrees Celsius minus 121 degrees Celsius divided by 10, plus this is for the third data point, 20 minutes into 10 power 105 degrees Celsius minus 121 degrees Celsius divided by 10. So now when you sum up, the F naught is equal to 0.565 minutes. So this was asked 2 years back, that is in 2021. So the answer is option D. So the moment you are asked about, given the temperature versus time plot, you can either do a graphical method like this, where you plot L versus T and calculate the area under the curve, or you can use summation of L into delta T. If it is very confusing for you guys, you just proceed with this. When to take out delta T out and when not to, just proceed with this. Multiply L into delta T first, always, and then sum at each and every data point, you will get the F naught value. Moving to question 14. In a thermal processing of food, the initial microbial microbial population of 10 power 4 organisms per container is subjected to heating at 140 degrees Celsius for 60 seconds. So here we know what is N naught, which is 10 power 4. We know what is the temperature, 140 degrees Celsius. We know what is the time, 60 seconds. Estimate the spoilage probability at the end of the process. The decimal reduction time for the organism is D140, that is D at 140 degrees Celsius. Here it is not here, if you can see. The decimal reduction time at 140 degrees Celsius is 0.1 minutes. So given these values, what is the spoilage probability at the end of the process? So in this case, we'll be using a slightly different concept in the first order kinetics. So here N naught is 10 power 4 organisms per container. We are not looking at the absolute count. We are looking at per container basis. So N naught is equal to 10 power 4 organisms per container. Temperature is 140 degrees Celsius. Time is equal to 1 minute and D140 is equal to 0.1 minutes. So if you guys remember, we had an initial equation log N naught by N is equal to T by D. So where that was capital N and small n, capital N naught and capital N. that capital N is the absolute count. The moment you have something, the organisms per container or some kind of a concentration, you can multiply that, you can calculate the amount by concentration into volume. Or in this case, it is given organisms per container. So if you multiply the total number of containers, you'll get the total number of organisms. Is this part clear? We always need only the total amount of organisms. We do not need per container, we do not need per ml, nothing. So in order to remove that, we multiply this into number of containers. That is what we are doing here. Let's say R is the number of R is the number of containers. So R into N naught divided by R into N. So this is basic R into N naught, small n naught is basically capital N naught. R into small n is basically capital N. I hope this part is clear and not confusing. Basically, you have to substitute values in the term of counts and not in terms of concentration. So in this case, we assume we are given that only one, we assume that only one organism survives the entire batch, which means your capital N should be equal to 1. That is, a single organism survives. In that case, 1 by R will be equal to the chance of spoilage. That is the spoilage probability that is being questioned here. So the moment you have what is the spoilage probability, you are looking at something called 1 by R. And this is the equation that we will be using. I hope this is not too much confusing for you guys. So if R into N, that is a single microorganism survives when you account all the containers. If you have 50 containers, in all of the 50 containers put together, there is one microorganism surviving. So R into N will be equal to 1. So automatically this equation will be equal to F equal to D log of R into N naught. And here we know what is the time. It is 60 seconds is what is given in the question. Time T or F value is given as 60 seconds, which is 1 minute. We know the D value, which is 0.1 minutes. Into log R, we do not know how many number of containers that we are dealing with. But we know what is the small n naught or the concentration, which is 10 power 4 organisms per container. So with that we substitute here. So 1 by R, when you calculate, that becomes 1 by 10 power 6, which means that you had 10 power 6 containers with you, out of which in all those 10 power 6 containers you will have only one microorganism surviving. So the chance of spoilage is 1 in 10 power 6 cans. That one microorganism can still survive and multiply. That is actually called spoilage. So the chance of spoilage is 1 in 10 power 6 cans. Answer is option C. Is this part clear? The moment you have concentrations or number of cans, use R into N naught and R into N, where N, small n naught and small n are concentrations. Capital N and capital N naught are amounts. Those are two different things. And we do not know what is R here. That is what we needed to calculate. And the moment you have something known as spoilage probability, put R into N as 1. Because that is what is ideally preferred. You will be processing your food such that only one of so many cans will spoil. So R into N is 1. With that you proceed and calculate what is R, which comes out to be 10 power 6. So 1 in 10 power 6 cans will be spoiled, and that is the chance of your spoilage. I hope this is clear. Let's see if we have any questions different so that it's not too much. These are all questions that we already discussed before. You see a lot of repetition though. Okay, let's see. Okay, the Z value of a microorganism is 12.8 degrees Celsius. Find the equivalent process at 115 degrees Celsius, which will give the same lethality as the thermal process calculated at 121 degrees Celsius for 8 minutes. Basically, it means that there was a food that contained microorganisms that was processed at 121 degrees Celsius for 8 minutes. That resulted in a certain reduction in microorganisms. For the same reduction, what is the time taken at 115 degrees Celsius instead? That is what we need to calculate. We know the Z value given as 12.8 degrees Celsius. So the Z value here given is 12.8 degrees Celsius. T naught is 121 degrees Celsius. F naught, which is the time taken at, since it was at 121 degrees Celsius, I'm naming it as F naught or T naught, is equal to 8 minutes. We need to calculate at capital T equal to 115 degrees Celsius what is the equivalent time. So for this, we already know the formula d2 by d1 is equal to 10 power t1 minus t2 by z. This is the formula that we've been using so far throughout the numericals. But something that you also might remember from the first order kinetics, that d is directly proportional to f. So if you look at this problem, yeah, the same equation itself, you look, log n naught by n is equal to t by d or f by d. If d goes here, then d is actually directly proportional to f. That is what I've assumed here. So since d is directly proportional to f, you can also write, since we are dealing with a ratio here, d2 by d1 is also equal to f2 by f1, which is equal to 10 power t1 minus t2 by z. Since you can calculate for d value and so, but it is going to take a longer time. So for an and we do not know the d value at one particular temperature. We know only the f value. So in that case, instead of calculating d and then going to f, we can directly calculate what is the f value, which is f2 by f1 is equal to 10 power t1 minus t2 by z. So because f is directly proportional to d and inversely proportional to k, that is, the longer it takes to reduce the organism by tenfold, the longer is the process time to achieve the sterility. Faster the reaction rate, shorter is the process. So if the decimal reduction time, if the time taken to reduce the microorganisms by 1/10 is very long, then it means you will have to run the autoclave or the retort for a very longer time. So automatically F is directly proportional to D. But if your microbial death kinetics is very fast, then your time taken is very, very short. So F is directly proportional to D, but F is inversely proportional to K. So here I'm again substituting. Let's say I have the F value at 121 degrees Celsius, which is 8 minutes. I have the temperature 121 degrees Celsius and the other temperature T2 as 115 degrees Celsius. From there, I'll calculate what is F2. So F2 divided by 8, which is F1 in this case at 121 degrees Celsius, is equal to 10 raised to 121 minus 115 by 12.8, which is the Z value. From there also we can calculate the F value, which is 23.5 minutes. So this is also one of the equations that we can follow. So this is going to be pretty, this is a problem that we've already solved. Yeah, so the thermal death kinetics following the first order is given by one of the following relationships, where theta, let's say theta is the time. So which one of these is the correct option? if I say that the thermal death kinetics follows the first order reaction, which one of these equations can be used to describe that first order reaction? So this will tell you if you understood when to use log or when to use natural logarithm. So it is always safe to start from this particular point where dn by dt is directly proportional to n. Now if I remove the proportionality constant, dn by dt is equal to minus k into n. Minus here again stands for the death kinetics, that is the number of microorganisms reducing. So now if I integrate this from n0 to n and from 0 to theta given here, I get ln of or natural logarithm n by n0 is equal to minus k theta. And now if I take an anti-logarithm on both sides, we have n0 by n, that is I'm just flipping this. So n0 by n is equal to e power k theta, minus minus gets cancelled because of the flipping, and n0 by n is equal to e power k theta. So it is this. The answer is option A. So when to use negative, when to use positive, when is it n0 by n, when it is n by n0, whether it is logarithm, natural logarithm, these can be very confusing. If you find it confusing, better start from this step. So I hope this is clear. Any doubts? Okay, moving on to one of the a thermal death time plot is log D plotted versus log T, the plot of n0 by n versus time, log D plotted versus time, and semilog plot of heating time for inactivation versus temperature. What do you call as the thermal death time plot? So the thermal death time plot provides information about the time required to kill a microorganism in a particular food at variety of temperatures. That is, if you plot a semilog plot of the thermal death time, yeah, the answer is D. The semilog plot of the thermal death time versus temperature, then you, as we said, the inverse will be the the inverse of the slope will be the z value, but this particular plot is known as the thermal death time plot. This is known as option D. So you have something known as the survivor curve that we discussed previously. This is the thermal death time plot. Both are different. Moving on to last question. Calculate the sterilization value at 130 degrees Celsius if the thermal processing at that temperature results in 99.99% elimination of microorganisms. So we know what is n as a function of n0. That is 99.99% microorganisms have died. So you have 1 minus this value. So you have n is equal to 1 minus this value in times n0. So that will be your n. And we know the temperature 130 degrees Celsius. So what is the sterilization value? What do you mean by sterilization value? So sterilization value, also known as S, is equal to log n0 by n, which is your LHS in your first order reaction kinetics. So LHS all this while when we were talking about a log of n0 by n, That is actually known as the sterilization value. So that is what we need to calculate. So for 99.99% reduction of microbial elimination, what is left or what is surviving is n is equal to 1 minus 0.9999 of n naught, which is n is equal to 10 power minus 4 of n naught. The same thing now I substitute to calculate S value. S is equal to log of n naught divided by 10 power minus 4 times of n naught. N naught gets cancelled. So log of 1 by 10 power minus 4 is equal to log of 10 power minus 4. So that is equal to, so this becomes 4 times reduction, or 4 is the 4 log cycle reduction or sterilization value of 4. So I hope this is one of the concept that was remaining, sterilization value concept. So as you can see here, majorly we discussed what was the D value, what is Z value, what is F value, what is lethality factor, Arrhenius concept, Arrhenius equation, and then the sterilization value. So these are majorly the ones that contribute to majority of the problems in this week's syllabus. So I'll be uploading this PPT immediately on the NPTEL website. So you'll be probably able to access it in a couple of minutes or so. The YouTube video will be made available to you very soon. So is there any doubt?